Welcome to Summarize Science, where the latest breakthroughs in technology are made simple. Today, the focus is on a fascinating paper about how AI models can dramatically improve their reasoning skills. Most people think AI only gets better through more training data, but researchers are finding ways to make existing models smarter just by changing how they sample their answers. This paper introduces a technique that helps AI rethink its decisions at critical moments. To understand this, it is necessary to look at something called the power distribution, which upweights the most accurate paths an AI might take. However, simply picking the most likely path from the start is mathematically difficult and computationally expensive. In the past, when an AI wanted to try a different approach, it would just randomly pick a spot in its reasoning and start over from there. As shown in the comparison on page 2, this uniform cut method often just changes small, local details instead of the big decisions. The researchers propose a better way by identifying what they call entropy jumps. Entropy is basically a mathematical measure of how uncertain the AI is at any given step during its generation. When uncertainty spikes, it usually means the AI has reached a crucial fork in the road. By looking for these specific jumps in uncertainty, the model can identify exactly where it made a high-stakes choice. This might be something like deciding which proof strategy to use or which algorithm to implement for a coding task. The illustration in Figure 2 shows how a model can get stuck in one way of thinking if it doesn't revisit these early, big decisions. Think of it like a reasoning tree where many paths lead to different outcomes. The entropy-cut method allows the AI to jump back to the specific branches where a semantic decision was actually made. This prevents the model from wasting time on the leaves or the small details that don't change the final result. When tested across several AI models and difficult benchmarks like Math 500 and Human Eval, this method consistently outperformed standard techniques. It helped models solve complex math problems and write better code without requiring any additional training. Looking at the data on page 12, it is clear that this method helps the AI find higher probability, higher quality answers compared to traditional sampling. It effectively concentrates the AI's effort on the most promising reasoning paths found in the base model. Remarkably, as seen in the accuracy graphs, the model doesn't just repeat the same answer over and over, it maintains a healthy variety of solutions. This is important because it means the AI still thinks creatively while being significantly more accurate. Even though the process involves more steps, the running times remain comparable to other advanced sampling methods. This makes it a practical solution for real-world applications where both speed and accuracy matter. In summary, the key takeaway is that pinpointing uncertainty is a powerful way to guide machine reasoning. By focusing on critical decision points rather than random changes, AI can solve much harder problems more efficiently. This research provides a roadmap for test time scaling, where computers spend more time thinking about hard problems. In the future, this could lead to AI assistants that are much more reliable at solving math, science, and engineering challenges. It shows that intelligence is not just about having the right answers, but about knowing which decisions are the most important. Ultimately, knowing when you're unsure is the first step toward being right.